Without energy, the world would look a lot like this. It's cold. Nothing ever moves. So cold, in fact, that nothing could possibly move, ever. And you wouldn't even know it was cold, because the signals would never travel up the neurons to your brain. In fact, why not take it even further? Without energy, the world would look a lot like this. Oh yes, without energy, light would never propagate, and neither would gravity or temperature. It would not be hot or cold, because there would be no matter. In fact, the Big Bang would never even have happened. Energy is essentially the ability to do work. 1 unit of energy, a joule, is the amount of energy it takes for a 1 Newton force to move an object by 1 meter. On Earth, this translates to about the amount of energy it would take to lift a small rock of about 100 grams to a height of 1 meter above the ground. There are various forms of energy, some of which are imaginary, or ways of thinking about energy. The different forms of energy are highly interchangeable, and are really just different ways of calculating the amount of energy that there is. The 2 principal forms of energy that I will discuss in this discourse are kinetic energy and gravitational potential energy. Kinetic energy is the energy exerted by an object when it moves. Kinetic energy is commonly used when we want to calculate how much energy an object would apply or have just by moving, or when we want to calculate the amount of energy it would take to move an object from one place to another. We can calculate an object's kinetic energy by first halving the mass, and then multiplying that by the square of its velocity. Gravitational potential energy is the second form of energy, which I will discuss in depth in this lecture. Gravitational potential energy is essentially the amount of energy an object could have if it was dropped from a particular height in relation to its surroundings. The gravitational potential energy is the mass of an object multiplied by whatever the gravitational force of attraction is on whatever particular plane of existence you find yourself on at that moment, multiplied again by the height from which you are dropping the object. Gravitational potential energy can be used to calculate the amount of energy an object would transfer to the ground if dropped from a certain height, or in conjunction with kinetic energy for myriad other purposes. I will show you exactly what I mean thusly. How fast exactly do I need to throw this rock in order for it to just graze the rock outcropping above me? Because energy is not created or destroyed, the kinetic energy the object will have as it leaves my hand will inevitably be the same as the gravitational potential energy that the object will have as it arrives at the apex of its flight. In other words, Ek at the bottom will equal E/GPE at the top, or half of the mass times the velocity squared will equal the mass times the gravitational attraction times the height. Now you may notice mass is on both sides of this equation, which means it's totally irrelevant to the answer we want to get to. This is because no matter what the mass is, the kinetic energy at the bottom will always be the same as the gravitational potential energy at the top. So, if we change the mass, we do not change the fact that these equations are equal to one another. So by dividing both sides by the mass, we arrive at half of the velocity squared equals the height times the gravitational attraction. Now, if we want to arrive with a subject of v, we must rearrange the equation, which we often find the need to do in physics. Now, rearranging this gives us v, the velocity, equals the square root of 2 times the gravitational attraction times the height. Now, if we input the numbers into this, we get velocity equals the square root of 2 times 9.81 meters per second times 3 meters. Or, the velocity must be 7.67 meters per second as it leaves my hand. Now let us test this.